In this videocast, we'll take a look at some further applications of the ideal gas equation and apply it to some stoichiometry as well. We'll start with sample exercise 10.7 in your textbook, where it says, what is the density of carbon tetrachloride vapor at 714 torr and 125 degrees Celsius? Well, I want to do a little derivation for you first before we start this problem. We left off when we were using this equation, the ideal gas equation, PV equals nRT. But remember that moles, N, symbolized by N right here, is equal to mass divided by molecular mass. And so you can take this and substitute it in here for N, producing PV equals mass divided by molecular mass times RT. And if we rearrange this equation just a little bit, you can take and you can find a special quantity. Let's do this. Let's take and divide both sides by volume. And then let's take this side of the equation and multiply it by molecular mass divided by RT, which means we have to do that to this side of the equation as well. Multiply it by molecular mass divided by RT. Now, cancel the things that are similar on top and on the bottom of each other. The R's and the T's and the MM's go away on this side. Over here we lose the V's. And what do we have left? Well, on this side of the equation we have M divided by V. And over here on this side of the equation we have molecular mass times pressure divided by R times T. M over V, mass divided by volume, is given a special name. What do we call that? Well, it's also called density. So you can find the density of a gas just by rearranging the ideal gas equation to be molecular mass times pressure divided by R times T. Notice the units, though. The units for molecular mass are in grams per mole, and R is generally given to us in atmospheres times liters per mole times Kelvin. And so the liters will be our units of volume here, and our grams will be our units of mass. So the density of a gas is usually given in grams per liter. Watch these units, because when you plug things into this equation, make sure you've got things in grams and in liters. Let's go back to this question. Sample exercise 10.17. What is the density of carbon tetrachloride? The new equation that we just derived is that density is equal to molecular mass times pressure divided by R times T. Well, it's carbon tetrachloride, and if you remember your naming and formula writing, carbon tetrachloride is CCl4. So the molecular mass of carbon tetrachloride, when you add up 1 carbon and 4 chlorines, is 154 grams per mole. The pressure that it's at is 714 torr. R for torr now, the universal gas constant for torr is 62.4 liters times torr per mole times Kelvin. I don't think your textbook gives this to you in the sample problem. They have you convert the pressure to atmospheres. And then the temperature is at 125 degrees Celsius, so 125 plus 273. Remember, it's got to be in kelvins. So notice your kelvins cancel with your kelvins, your moles with your moles, and your torrs with your torrs, and you're given grams per liter as your final units for this. Multiplying the top and dividing by the bottom, you end up with 4.43 grams per liter. That's a simple plug and chug use of the density equation from the ideal gas equation. Let's look at the next sample exercise, 10.8. A series of measurements are made in order to determine the molar mass of an unknown gas. First, a large flask is evacuated and found to weigh 134.567. It's then filled with the gas to a pressure of 735 and 31 Celsius and reweighed. Its mass is now 137.456. Finally, the gas is filled with water at 31 and found to weigh 1,067.9 grams, and the density of water at this temperature is not quite 1. It's a little bit less. Assuming that an ideal gas equation applies, calculate the molar mass. So now we're going to be looking at something like this, except we're not solving for density this time. We're going to be looking for molar mass. Okay? So the things that we're going to have to look and see if we can find if if we just rearrange this equation, our density, we're going to look for pressure, and we're going to look for temperature. And I think all these things are available, even though that was a very wordy question. First, let's find the mass of the gas. And if we find the mass of the gas, we have to take 137.456 grams, subtract from that the 134.567 grams. This is the mass of the empty container. This is the mass of the full container. So our gas ends up weighing 2.889 grams. Now to find the density right up here, remember that density is equal to mass divided by volume. I now know the mass of my gas. I need to find the volume that that gas occupied. Well, there's a clue to that too. They filled the container with 1,067.9 grams of water, and they tell us the density of the water. Remember the triangle? Density is equal to mass divided by volume. If I know my density and my mass, guess what I can find? Well, I can find the volume of that container. So volume will equal my mass. Turned out to be, let's see, the mass of the water. So 1,067.9 grams, and I subtract from that the mass of the container, which was 134.567 grams. Take those as my mass and divide it by my density. My water is 0.997 grams per milliliter. This will give me my volume in milliliters. And so it turns out to be, my volume in milliliters, which turns out to be, my density, in grams per milliliter. And I converted it right away to liters, and it turns out to be 3.09 grams per liter for the density. My volume, yes. The volume ended up being, I went one step too far. The volume ended up being 0.936 liters, which is 936 milliliters for a volume. Now I can plug it into the density equation. Density is 2.889 grams, and divide that by my liters, which is 0.936 liters. And now I get the answer of 3.09 grams per liter. Sorry, got ahead of myself just a little bit. Now that I know the density of the gas, now I could plug it into this equation right up here, where I know the density, I know the pressure, and I know the temperature. And I'm going to be a little short on space. I'll see if I can fit it down in here. If I want to know the molar mass will be equal to, rearranging this equation, density times R times T divided by my pressure. My density is 3.09 grams per liter. My R, I'm going to run out of room here. I'm just going to write this down below here just a little bit. Molar mass is equal to 3.09. Notice it's in grams per liter. My R that I'm going to use here, my pressure is given to me in torr. So I'm going to use 62.4 liters times torr per mole times Kelvin. And my temperature is given to me is 31 degrees Celsius, which is 304 Kelvin. And I'll divide by my pressure, which is 735 torr. Notice my torr cancel with my torr, my liters go with my liters, my Kelvin with my Kelvin, and I've got grams per mole left for molar mass. Plug those into the calculator, and finally we end up with 79.7 grams per mole. 79.7 grams per mole. Going on to the next sample exercise, 10.9. I kind of scribbled on that already. But we can see that the safety airbags in automobiles are inflated by nitrogen gas generated by the rapid decomposition of sodium azide. Azide, N3 minus 1, is a polyatomic ion that perhaps you've never seen before. Okay, deal with it, like it. If an airbag has a volume of 36 liters and to be filled with nitrogen at a pressure of 1.15 atmospheres at a temperature of 26 degrees Celsius, how many grams of NaN3 must be decomposed? So now we're doing a stoichiometry type problem, and we want to find this right here, the mass of this. Well, first of all, what we need to do is we need to find the number of moles of nitrogen that we need to fill that. So let's use PV equals nRT, and let's solve for N. PV equals nRT. N would therefore equal PV divided by RT. My pressure is 1.15 atmospheres. My volume is 36 liters. R here, I'm going to use 0.0821 liters times atmospheres per mole times Kelvin. And my temperature is 299. 26 degrees Celsius, so 299 Kelvin. When I do that, my number of moles turns out to be 1.7 moles of N2. Well, now that tells me how many moles of nitrogen need to be decomposed. From this, how can I find out how much sodium azide I need? Well, the relationship here is for every 3 nitrogens, there are 2 sodium azides. So a 2 to 3 ratio, multiply those together, I end up that I need 1.1 moles of NaN3. I can convert that to grams. It turns out that there are 65 grams in a mole, so I multiply this by 65 grams, and you've done this part a lot of times before. It turns out that you need 72 grams of the NaN3. There we go, a little gas stoichiometry problem. Let's go on to sample exercise 1010. This one says a gaseous mixture made from 6 grams of O2 and 9 grams of CH4 is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas, and what is the total pressure in the vessel? This goes back to a special law called Dalton's law of partial pressures, where the total pressure inside of any container is equal to the pressure of each gas that makes up that vessel. So if you've got 2 or 3 gases, you have to add the pressures together, and it gives you the total. Not hard. And you can treat each gas independently and then add them up at the end. So we're told that we have 6 grams of oxygen, and we're also told that we have 9 grams of CH4. Converting this to moles, in 1 mole there are 32 grams, and this tells me that I have 0.188 moles of O2. It also tells me that there are 16 grams in 1 mole of CH4, and this would be 0.563 moles of CH4. Well, from this, since I know the number of moles, and I know that the vessel is 15 liters, remember the gas fills the space of its container, so each gas is going to fill 15 liters, and they're all at 0 degrees Celsius, now I could find out the pressure that each gas exerts inside that container. Pressure is equal to nRT divided by V, and I'll have to do this for O2, and I'll also have to find the pressure for CH4, which will be equal also to nRT divided by V. The volumes will be the same for both of them. The temperatures, of course, will be the same for both of them. The only difference is that we'll have a different number of moles of oxygen gas and a different number of moles of CH4 gas. So, putting in these numbers, I have 0.188 moles of oxygen gas. My R, let's see, does it ask for a specific type of pressure? I don't think it does, so let's use atmospheres. 0.0821 liters times atmospheres per mole times Kelvin. And the temperature here is 273. Divided by the volume in this case is 15 liters. On the bottom here, I have 0.563 moles of the CH4 gas. Same gas constant, 0.0821 liters times atmospheres per mole times Kelvin, and 273 for a temperature, and divide it by 15 liters. Remember, each gas occupies the entire container. You can't say that one gas only occupies a certain portion of the container. They both fill the container. That's one of the properties of a gas. It turns out that this one is 0.281 atmospheres, Oops, running out of room here. And this one is 0.841 atmospheres. These are the partial pressures of each of the gases inside of the container. And if you wanted to know the total pressure of the vessel, you simply add them together. And you end up with a total of 1.12 atmospheres for the total pressure inside the container. Let's move on to a few other sample problems. Let's look at sample exercise 10.11. A study of certain gases on plant growth will require a synthetic atmosphere composed of 1.5 mole of CO2 and 18 mole percent O2 and 10.5 mole percent argon. Calculate the partial pressure in the mixture if the total pressure of the atmosphere is supposed to be 745 torr. Well, we're back to partial pressures again now. And it wants to know the partial pressure of the oxygen gas in there. Well, since we're told that 18% of it is oxygen, that means that 0.18 of one whole atmosphere is O2. And we're told that the whole atmosphere is 745 atmospheres of pressure. Multiply those two together, and it turns out that there are 134, whoops, I think it didn't give it in atmospheres. I think I wrote this wrong. I think this is 745 torr. This should be torr, sorry. 745 torr. Multiply those two together, and 134 torr are the partial pressure of O2 inside of this atmosphere. Letter B, I think there's a typo in your handout, but you can just fix it. If this atmosphere is to be held in a 120 liter space at 295 Kelvin, how many moles of O2 are needed to fill this space to cause it to have 134 torr of partial pressure of oxygen? Well, we know that the partial pressure of oxygen is going to be 134 torr to make this happen. Okay. What we need to know is how many moles of this oxygen I'm going to need to fill this. Well, if I use PV equals nRT, I can solve this in terms of moles of oxygen. N is equal to PV divided by RT, and the pressure here is the partial pressure of the oxygen, 134 torr. The volume is 120 liters. R has to be in terms of torr again, 62.4 torr times liters per mole times Kelvin. This is a handy number, but it's not given in your textbook. They usually have you convert it to atmospheres first, probably because on the AP exam they don't give you the 62.4 as well. And 295 Kelvin, I believe it has to be held at. When you multiply these together and do your division, it turns out that you would need 0.872 moles of oxygen. 0.872 moles of oxygen. Let's look at sample exercise 10.2. A sample of KClO3 is partially decomposed, producing O2 gases that collected over water, as in figure 10.16. Oh my gosh, what is figure 10.16? Well, I'll save you some time here. The picture actually looks like this. Oops, if I can get this to fit. Here's my picture. And you can see, if I zoom in just a little bit, oops, that's out. Okay. Maybe I can't zoom in quite so far. But you can see right here is the gas collection going on, and we've got a tube that comes down here that's producing gas. And actually, I think they tell you right here, this is a substance that's heated like KClO3, and it gives off the gas. Notice it bubbles into the water, and the water, of course, is displaced by the gas. So the total pressure right here inside the container is equal to the pressure of the atmosphere as long as the water levels are equal to one another. If you push it down further, of course, the water pushes up and squishes the gas inside of the container. Or if you lift it up too high, then, of course, the pressure inside of here is less. Well, let's take a look at this question where they said the gas is collected over water. That's what that's called. And it says the volume of the gas collected is 250 milliliters, or 0.25 liters, at 26 degrees Celsius and 765 torr total pressure. How many moles of O2 are collected? Well, first of all, you have to realize that inside of that container, there was a picture of a little beaker like this, and then what happened was there was a beaker that was upside down, and the gas bubbled into the beaker, and then what happened was the water level came down to here. Of course, there's water inside of here as well. This gas that's inside of this container not only has the oxygen gas that's in there, but it also contains some H2O gas, sometimes known as water vapor. And depending on what the temperature is, the water vapor can vary how much water vapor is in there. And so what you need to do before you can find the moles of O2 is to subtract out the pressure caused by the water vapor. So we can write an equation where you can say pressure total, from Dalton's law, is equal to the pressure of the oxygen gas plus the pressure of the H2O vapor or gas that's inside of the container. Well, it tells us that the gas is collected at 26 degrees Celsius. When you collect gas at 26 degrees Celsius, the pressure of water vapor at that particular time is 25 torr. Well, you need to look that up in the textbook, or at least have it told to you in the problem that that's the water vapor pressure. There are tables of water vapor pressure, and I believe there's one in your textbook somewhere. Might be a nice thing to search for. Well, we want to know what the pressure of just the oxygen is. We know that the total pressure, of course, is 765 torr. And when you do the math here, it turns out that 765 is equal to the partial pressure of the oxygen plus 25. Solving for the partial pressure of the oxygen, PO2, turns out to be 740 torr for just the oxygen gas. Now, we wanted to know the number of moles of oxygen in there. And if you use N equals, PV equals nRT, so PV divided by RT, we can put the pressure in here now of the dry oxygen gas, which is 740 torr. The volume, that stays the same, right? That's 0.250 liters. It doesn't matter whether it's got water vapor in it or not. The gas fills the shape or size of its container. This is 62.4 liters times atmospheres per mole times Kelvin. And, whoops, I said that wrong. It's not atmospheres, it's liter times torr. That's what the 62.4 allows us to do to cancel the torrs. Maybe if I write it a little more scribbly, it'll look like I wrote torr. And then the temperature, of course, was 26 degrees Celsius, and if you convert that to Kelvin, it's 299 K. Multiply the tops and the bottoms, and it turns out that there were 9.92 times 10 to the negative third moles of oxygen collected. Letter B, how many grams of KClO3 were decomposed? Well, KClO3, when it's decomposed, gives us oxygen gas, and it also gives us some KCl. When you balance this chemical equation, I think you need a 3 here, and a 2 there, and a 2 there. And notice the ratio between KClO3 and O2. Now, if you know that there were 9.92 times 10 to the negative third moles of oxygen produced, you should be able to multiply a ratio of O2 to KClO3. And the ratio was 3 to 2, a 3 to 2 relationship, or a 2 to 3 if you want to read it top to bottom. Multiplying those together, let's see, it asks for mass, of course. I'll just continue on here and find out the mass. Grams of KClO3 in moles of KClO3. When you add KClO3 up on the periodic table, it turns out to be about 123 grams, and you end up with approximately 0.811 grams of KClO3 that was decomposed to give you this amount of oxygen gas.